Okay, I tried doing a video before and it was way too long. So unfortunately I don't think I'm going to be able to do the full interpolation video, so instead I'm going to try doing interpolation abridged this time. This will be me talking extremely fast in an attempt to not abridge too much, but I will have to leave some things out and maybe we can discuss those later, either online on Twitter or something or via email. If anyone has any more questions then I can post some follow-ups. Okay. So what is interpolation? What do I mean by that? Well, in the grass algorithm, when I was talking about planting the grass algorithm, I mentioned a bunch of times that there are ways to control, for example, the size of the grass. And I showed a video where you could do this sort of thing. And you saw something where, you would put some grass down and you would be planting the grass around it. And the algorithm would be changing the size such that, for example, things close to the center of the grass would be large and things towards the edge of the grass would be tiny. And in between, the artist would be able to control sort of how that was, where everything tiny, right up to the point where it got right next to the center and then they got big? Was it looking like that? Or was it looking more like everything was big and then it suddenly gets tiny right at the edge? Or was it something that was more smooth? So it's tiny at the edge, large between, and each step gets smaller and smaller and smaller in kind of continuous fashion, right? All of these things are places where interpolation code has to come into play. Basically, the artist is not going to specify in any given scenario the size of every single thing when you're talking about something like this grass algorithm where you have to have things distributed cleanly. And so if you're going to be distributing that many things over a surface, you have to have some way of them giving guidelines to the algorithm that allow the algorithm to pick values everywhere, even though values have only been specified in some small number of places. So for example, in the grass algorithm, they specify a value at the center, they specify a value at edges, and then in between they can control it using something that generally is referred to as a fall-off. And the only reason it's really called fall off is because it tends to be something that, for example, with the size, it's like, oh, it starts big and then gets tiny, right? If you look at it, it kind of goes off. If this is, maybe a graph of size, let's say, versus distance from the center. So the question is, if we want to make things like this, where the artist can control what's going on, how do we give them convenient controls for doing that? Something that allows them to shape this curve into something that they, that is pleasing. How does this curve even exist in the code, for example? There's another place inside the grass planting algorithm that I'll touch on later that also uses interpolation in a different way, although with the exact same construction, and it will be interesting to see that, so I'll kind of talk about that later to give you a little preview of what that is. There was another way in the grass system in the witness that people could control things like size, and that was by painting. So they could actually have a bitmap that they would load in that would kind of get laid over the grass surface, and the colors at the various points on the bitmap would determine how big or how dense the grass was and things like this. Okay, so let's talk about this part first. Let's talk about the curve first. All right, so the first thing that we need to talk about is how do we sort of interpolate things in general? How do we take 1 or 2 or 3 or 4 examples, however many we're given, and produce a whole range of values that encompass the space between those examples? So I want to start out by talking about the most simple thing that you might ever want to do, which is if someone gives you a point, I'm going to call this point P0, right? It's a nice little point floating in space somewhere. I don't care how much dimension this is. This could be 1D, 2D, 3D, whatever. I just got some point in some space, and I have some other point in some space, P0, P1. Basically, the most simple thing you might want to do with interpolation, really basic linear algebra here, is that if I wanted to construct a function that moves between P0 and P1, I could do that very simply by looking at the vector from P0 to P1, and this vector here, this delta P, if you will, that delta P is like one of the simplest things that you might ever compute in linear algebra. It's just P1 minus P0. That is the way to get the vector that goes from P0 to P1. Very simple. So if I wanted to construct a function that moves me continuously from P0 to P1 so that I could generate any point in between that I wanted to, it would be very simple. I would create this function. I'm going to call it b of t. B I'm going to use because blend, and I kind of like B rather than F sometimes because, hey, all functions are Fs. Let's give it something different. Okay, so I'm going to create a blending function, B of t, and the t that I'm going to pass in here is going to be a parameter that I can vary, that I want to be able to vary such that I can produce points anywhere in between these two. Well, since I know that I have this sort of difference here, this vector that moves me from one to the other. It's very simple for me to construct a function this way because I can always just start at p0, I can start here, and then I can add however much I want of this delta p vector, right? I can do the parameter I pass in times the delta p vector, which will move me in this direction, right? Because if I start here and I always move along this vector, then I'm just going to get movement this way, and the greater the t value is, the further I'll move this way. Okay, so what is this t parameter? What are its values? Well, it's pretty easy to just look at this and immediately tell what the bounds and range of t are and what it means, because if I look at p0 and I say, what would it be if I just wanted to be right at p0? I wanted to start at the first point that I was given, I wanted to produce that. Well, that is p0. So all I want to do is knock out the delta p term entirely. So that means that b of 0 equals p0, because this term goes away, right? So a t value of 0 starts me at p0. Similarly, if I want to get to p1, well, I know that this entire vector, if I used the complete vector, that would get me from p0 to p1, because that's exactly what it was. So b of 1, if I just use the unity for this, 1 delta p, I know I will get to p1. And of course, I can actually plug this in to verify. If for some reason you did not believe me, 1 times p1 minus p0, well, hey look, I've got a positive p1 and a negative p0, the p0s cancel, and I'm left with just the p1, right? So I can see just from this simple construction, it's very, very straightforward, that I can produce something that gives me values in between these two by saying that I have this b of t, it's equal to p0 plus t delta p, right? That's my little function. And if I say that t goes from 0 to 1, right? That is the range in which I can produce values along this line. Now obviously I could continue, I could use negative values and get out this way to go further outside of it, and I could use values greater than 1 and get out past it this way. But since we're talking about interpolation here, I really don't want to necessarily do that. I'm trying to keep inside these two, as we'll see in a second when we start to actually use this for something. But you can see how the actual same equation can use for extrapolation just fine. Alright, so let's take a look at this b of t that we just constructed, right? We've got b of t equals p0 plus t times delta p. Well, I said that this delta p was just p1 minus p0, right? So what I want to do is I want to look at this equation, what happens if I get rid of the delta p so that I can just express it entirely in terms of the input points. Because that's a little bit easier for me to work with since I don't introduce this synthetic variable all the time. So what I can do is I can just substitute that back in, right? I can just say p0 equals t times this quantity right here, right? This quantity p1 minus p0, okay? And this is a new equation that no longer has a delta p in it because I replaced the delta p with what it actually was. If I multiply that out, I get a nice convenient form for this equation, right? T p1 minus t p0, and grouping the terms, we get the p0, there's two of them, right? So it's 1 minus t p0 plus t p1. Alright? Makes sense? Now, for those of you who already know all this stuff, obviously, well, I don't even know why you're watching the video actually, because it's an introductory video and you're probably going to be very bored, but this is a very standard equation that you often see. This is basically the standard linear blend equation. So when people talk about linear blending, if you've seen that before but weren't quite sure what they were talking about, this is the equation that they're usually talking about. They are talking about 1 minus t times one input and t times another input, and by ranging t from 0 to 1, you basically blend between these two. Why is it linear? It's linear because we are moving along this line here, and we are moving along it in a linear fashion. Every increase in t, if we increase t, say, by 0.1, we would move 1/10 of the way along the line. We increase it by 0.1 again to 0.2, and we move 1/10 of the way along the line. It's always the same distance for every change in t. If it was non-linear, that wouldn't be true. We'd move like slowly in 0.1s, and then all of a sudden 0.1s would move us a lot or something. There would be inconsistent motion along the line if this were non-linear, but it is linear, obviously, because, hey, if you look at this equation, there's no t squared, there's no t cubed or anything. Everything is linear because everything is to the first power. Okay, and we're going to see a little bit more about that as we move along. So given this linear blend, we can already do, just this by itself, we can already propose one solution to the grass planting situation that we talked about before, right? I said I have a center point for my grass. We're going to call this P center, for example. And I have, sort of a distance out here that I'm planting the grass. The grass is coming in here. Here's my happy grass. And for any point on the grass, I want it to go between two values, one that's specified at the center and one that's specified, say, out at the radius distance, PR, let's say. And for purposes of this, since we're talking about distances, since I don't care really where it is, we can almost say, well, we don't really care about the points per se. So in some sense, we're not really going to define these in space. What we're really talking about is just how far away they were from the center, right? So we're really just talking about a distance here. We want to measure the distance, and then we want to blend some values that are based on how much that distance is. So if something's right at the center, if something's at PC, for example, right? So let's say I'm taking a grass point and it's very close to P, then its distance will be low. And if I take one that's out near the full radius of the grass, then its distance will be high, and I want to use that distance value basically as my t value. I want to plug that in, and I want to blend between two other values that are representing something in the grass system, such as the size, right? So how would we write something like that? We basically want a size function, right, that takes as a parameter the distance, and we want this to be a function that we can easily control and then output something that we want. So we want to be able to input something like the size at the center and the size at the outside and have that give us something that we want. Well, we can basically start to propose something now just using this equation. We could say that the 2 points that we're going to blend between are two sizes, right? So instead of them being points in space, they're sort of points in our size space, if you will. We can blend between those two. So we would have something like, size of t equals 1 minus t times the size at, say, the center, plus t times the size at the radius, right? This, we just saw, is a way to smoothly go from one size to another size, or really any two values. And so all we would have to do is figure out, well, how do we get t? What is the t that we plug in here, right? Okay. So how do we get that t? In order to get that t, we already said that t must go from 0 to 1, right? We want that to be the case for the blending equation that we worked out. And the reason that we wanted to do that is because we said it starts at P0 when t is 0 and it ends at P1 when t is 1. So if we want to stay in between the two size values that the artist specified, we must stay in this range. If we started going outside of that range, things would be bad because we'd start going to sizes that were outside the sizes that the artist actually specified. So the first thing that we can say is that we are going to have to clamp our t, right? So this size function, when we say, size of t equals 1 minus t times size at the center plus t times size at the radius, the artist specifies the size at the center, size at the radius. We can interpolate between them. We have to make sure that this is well conditioned and it meets this criteria. So the first thing that we're going to do before we call size t is just clamp it. We're just going to say if the t is less than 0, then t equals 0. If the t is greater than 1, then t equals 1. We're just gonna clamp it. Now, you might say, well, why do you have to clamp it? Because in any artist-driven situation, in any editing package situation, it's very typical where you're going to have not well-conditioned inputs because things get edited and you want to allow flexibility and all that sort of thing. So it's typically safest, even after we do the math here at the when we're actually work out the rest of this, it's probably just a good idea to always clamp when you're working with something like this because you never know what's going to happen, really. You never know how the code's going to be edited. So we'll look at that in a second, a little more detail. But for now, let's just say we're going to want to clamp our t's. And why are we going to want to do that? Well, no matter what we do, we're going to be asking questions of this size function, and it's possible that people might start asking for sizes when they're outside of the grass planting region, or who knows what else might happen, and we want to make sure that we always get back consistent results, so we're just going to do that clamping. All right, so the next question is, if we have the clamping though, we said that we had a point at the center that's the center point here, right? And then we said that we had a radius, right, some r distance that goes out to how far grass can be planted, and we're planting the grass in between it, and we say for some point here, for some grass point, p, we want to actually figure out what is the size value at that point. We want to ask that question. Well, we can't just say what is the distance between these two. We can't just say subtract the center, let's say, you know, take the distance from here to here, right? We can't just say that because this is some value that's actually in world units. Like this radius value, right? This radius value could be like 30 meters or something, let's say. That's how big the grass planting region was. So this right here, you know, that could be something like 20 meters. So when I take that length, when I say what is the distance, right? When I, you know, however you want to compute that in your thing, it's, you know, it's the length of the vector of p minus the center point, right? So when I get that length back, it's going to be something like that's going to be 20 meters, right? So I could clamp that, I could pass that into this thing, if meters is our unit system, and I could clamp that and I would get one would be the value that I'm going to be passing this thing. So that would immediately be, right, at the radius on the outside, that would be at the radius size. It would instantly clamp it right up to the size that the artist specified they want the radius. But that's not where this point is. It's not there, right? It's got a ways to go. And the reason for that is because the scale, right? This is not going between 0 and 1 at all. It's going between 0 and 30. So the distance is in a space that is totally different. It's at a scale that's totally different from the t space that we wanted. We have something going from 0 to 30, and we wanted something that goes from 0 to 1, right? Now that's really simple to solve for, but of course, if you haven't done that before, it's probably a little confusing. Really, all we need to do is normalize this. We want to turn our range from something that goes to 30 to something that goes to 1. And that's extremely easy to do because all that is just a divide. It's just a divide by the maximum value that we have. So we have a 30 here, we have 30 meters. We just need to divide by the 30, and that will normalize our 30 to 1 and everything in between there to, you know, whatever it needs to be. So for example, at 15, right, we wanted that to be 0.5, but it's at 15 meters. Divide by 30, you get 0.5. Same thing at 0.25, same thing, right? It works to normalize this range down to something that is in 0 to 1. So all we have to do is basically say when we want to call our size function, we just first take our t, and our t, you know, we will assign t divided by the radius, whatever that is, which gives us a value between 0 and 1, just in case somebody was giving us something outside that, you know, somewhere out here, or heaven forfend something negative, which I don't see how they could do because distances are always positive, but, you know, who knows what happens. We're going to clamp it just to be sure so that we never erroneously, you know, output a value, and off we go. We compute this, and that's the entirety of, that's all the work we need. Now the artist can specify SC, which is the size at the center, and they can specify SR, which is the size at the radius, and they're done. Perfect. They can control it. Everything's great, right? Everything's happy, and in fact, this is exactly what the original grass planting code was doing before I went in and added the fancy, quote-unquote, fancy stuff. But the artists wanted more control than that. They wanted more control than this equation. And why did they want that? Well, the reason is back when we looked at this thing before, when I first started saying, what are the options here? If you remember, I kind of drew a couple different things. I said, oh, you might want them to kind of continuously fall off the sizes. You might want them to start big and get small. You might want them to get small slower. And what you're really talking about there is having control over something that is not linear. It is not progressing in a constant step as you go, going from big to small or whatever it's doing. It's something that looks like these curves that I was drawing that says, you know, oh, the size starts out big and it kind of eases down to it, or maybe it stays this way and then dips down, or maybe it dips down very quickly and then stays small. These are the sorts of things that we want to be able to do. So in order to do that, this equation that we have here, this one here that we created, the b of t, that guy, is simply not sufficient. It's not going to cut it. We need more controls. We need to pass something more. And so if I talk about this a little bit more explicitly, and I say what this b of t is, you might say that it's b of t p0, p1, right? We might say, or, you know, honestly, I actually usually like to write it this way just because I think of it this way, but I usually write it b of p0 t p1, which is to say that t is a thing that goes from 0 to 1 and moves me from p0 to p1. So I usually order my parameters that way, but you can order them however you want. Point being, b is a function that is basically going to take two example points, I should say, two example points and a t, and it's going to give us a blend between those where 0 is the first one, 1 is the second one, and we can get anywhere in between. Okay, that's a good thing, that's what we want. But we now want more control over how that happens. So the question is, how do we get that more control? How can we produce something that's going to be more flexible and has some more parameters to it so that you can make those sort of curve shapes? Well, you've all seen sort of the textbook standard way of doing this before. You've all experienced these in art packages everywhere. When you get curves, when you want to make curves, you always see you get these things where they're like, okay, you know, here's a point, right, and I've got another point over here that you know, I'm dealing with or whatever. And then in addition to those points, there are these tangent handles. They're always called tangent handles, right? They're these things that kind of pass through the points, and then the curve, whatever it's doing, does this thing where it kind of like goes through the tangent handles, right? It kind of bends to them, such that if you stretch out the tangent handles, you know, it gets kind of elongated. If you shrink them, it gets tighter, and you can change the angle, right? That sort of stuff. And these are called Bezier curves, right? I don't know why they're called Bezier curves, because Bezier didn't invent them. I guess Bezier was kind of like the guy who popularized them, right? He's kind of like, he's good at selling things to the press. He kind of, you know, I don't know what you want to call that. Maybe let's say he Molyneuxed, you know, he was the Molyneux salesman of this sort of thing, where he kind of convinced everyone that these things were awesome, because they were really developed beforehand by DeCastle Joe and some other guys. I don't know. You can go on Wikipedia and read the history of it. I'm not a good math historian. I never know what's going on. But point being, they are often called Bezier curves, and you've seen that a lot. They are not invented by Bezier, but who cares? All right. So the question is, these Bezier curves that you see, that we've all kind of standardized on, they are very convenient. They're just one mathematical construct that people have found that's very easy to tune. It has reasonable ways of thinking about its inputs that are a lot easier than just some crazy equation that you see that's like, oh, you know, it's the t cubed times this plus I over 4, whatever. Like, there's plenty of weird mathematical curves we could come up with, but the Bezier curves happen to be ones that are very easy to control and have, you know, found favor among artisanal uses and draftsman uses to produce curves that people can actually edit. Okay, so how do we create Bezier curves? What is a Bezier curve? What is a good way to think about it? How can you remember it? How can you code it without, for example, typing Bezier curve in and cutting and pasting someone's code off a Stack Exchange, which I guess is a totally legitimate way to go, but assuming that you want to be one of those people who actually knows what's going on, how do you become that person? How do you become that person? Well, the answer is, Bezier curves are very easy to understand if you think about them geometrically. They're extremely easy to understand. What we're going to do is we're going to say that yes, we want to be able to specify these two tangent handles, so what we need are two additional points. We need two additional points besides the points that we are trying to interpolate. So we start off with P0, and then we have another point, which I'm going to call P3, and in between there we're going to introduce two more points. Okay, so we're going to introduce P1, and we're going to introduce P2, so that now, instead of interpolating between P0 and P1, we're going to interpolate between P0 and P3, but we are going to use these additional 2 points to guide us, so that we can move them around and change the shape of the interpolation. Instead of just going directly like we did with the delta P, we're going to go ahead and go in some kind of a nice curved fashion. So the beautiful thing geometrically about Bezier curves is that if you understood that first equation, if you understood that nice little B of t equation where I did B0 t P1, and it was equal to 1 minus t, P0 plus t, P1. If you understood that little guy, and he was solid for you, then you'll have no trouble understanding Bezier curves right off the bat. All a Bezier curve is a bunch of these. It's just a bunch of these evaluations that are done recursively. So to create a Bezier curve, what you can think of doing is you can think of it being a scaffolding, basically, of line segments that connect the points together. And what we do is we start with the full set. So there's 4 points, so I have 3 line segments. We evaluate a single t. So we're going to do just like before when we said we're going to pick a t, the t will move us along our curve. So we're going to have t equals 0 is going to be at P0, t equals 1 is going to be at P1 just like before, but now we're going to create a function which moves us along the curve. Okay, it moves us along the curve as we move that t. The way we're going to construct that is just by doing this function on our 3 line segments. Okay, so let's say, for example, just because it's the easiest thing probably to draw, let's say that our t was 0.5, so it's halfway. Well, okay, halfway along each of these by using our previous thing would produce these 3 points. We know how to do that. We'd just apply b to this, we'd apply b to this, we'd apply b to this, each time with the same t, 0.5. We would get these points. Next step, connect the points, right? Connect the new points that I made. Recursively apply the exact same logic. Scaffolding you have here, these new points, apply the same t, connect the points. Finally, last one, all you have to do is apply t because you're only going to get 1 point. That is the point on the curve. That is literally the entirety of understanding how a Bezier curve works. If you just want to kind of see the geometry of it, that's all you need to remember. If you can remember this, I will show you how to create the equations from just that very, very, very simply. There's a number of ways to do it. But you could even do it even just by saying that, right? Even now that you know that, you probably could go work out the equations yourself because I just told you all you do is you apply b, you just apply it to each one of these and apply it recursively. It's very, very, very straightforward. Okay, so does that make sense? If you think about it, and there's probably some nice animation online somewhere, I hope. The only thing I can't do on this paper is animate, unfortunately. But hopefully you can see that since you're using the same t all the time, basically what happens is you start out with a point here because all of these are collapsed this way. You're at here, 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 and everyone's back. As you go, this scaffolding kind of rotates around, and this midpoint here, which starts off here, kind of traces out the curve, almost like a mechanical, kind of like a sliding mechanical movement, if you will. And so it's actually kind of a little bit tricky to visualize in your head how that's actually working, why it produces the curve without seeing it animate, so I apologize for that, but that's the one thing I can't do. Point being, this geometric construction, if you can remember it, is all you really need to do to be able to back solve, I shouldn't say back solve, to basically back up and figure out exactly what the equations are. All right, so let's actually do that. Let's actually figure out how we want to write that. Well, I could do it the straightforward way, and this is the way I was saying you could probably do yourself, which I could say, okay, I've got a b, I'm going to apply first to each of these. So I'll have 3 of them. I'll have b of p0, t, p1, I'll have b of p1, t, p2, I'll have b, p2, p3, right? So this guy is here, this guy is here, and this guy is here, right? These are the 3 of those. Then I would just need to b up both of these guys. So I would need to then say, well, okay, I got the results of these 2 guys, right? Which is this point, and I need to b those again. So I need to apply another b, right? And the same is true of these 2 guys here. So this middle guy is shared. I've got to do b again. I've got to do it to these 2, right? And then those 2 points, which I produce from those, I've got to do it one more time. Right? So I'm basically applying b, if you could see, it's kind of like a triangular reduction, a binary reduction each time. I'm kind of shrinking by 1 because I'm blending the results and blending the results, right? So rather than actually apply this out recursively, which would take a really, really, really long time to write on this paper, we can do something much, much simpler. Instead, all we really have to do is actually just look at the triangle, right? Each one of these little tree, I should say, that I was making, each one of these is just a b between the points. So I could have instead just written it as a b with, p0 here, p1 here, right? p2, p3. So I could really write the whole thing as that if I just wanted to write it this way. So let's just do that, right? Let's actually just do p0, p1, p2, p3, and imagine applying b this way. So to get my final point, I just b each pair, I b the results, and I b the results one more time, and there I go. Okay, how does that help me get the equation faster than actually doing the b the whole time? It helps me because if you think about what this is actually doing, these are multiplies, okay? The b function is just a 1 minus t. Sorry, I moved that out of the way a little bit. The b function is just a 1 minus t times the first input and a t times the second input. So each time, whatever the input is, whatever the thing that's coming up the branch for me, each time the thing coming up the branch is just getting multiplied by either 1 minus t or t, right? So if I look at this pyramid over here, the only thing that I'm really saying is, well, the branches that go this way, these branches are multiplies by t, right? And the branches that go this way are multiplies by 1 minus t, right? 1 minus t, 1 minus t, okay? So what's that? That's a t branch, right? It's going that way. What's that? That's a 1 minus t branch, right? What's that? T branch, 1 minus t branch, 1 minus t branch, right? Makes sense? So really all I'm doing is multiplying up. That's all I'm doing. So I can read off the equation for p by literally just summing all the different routes through this tree. That would be all the terms that I ever got, right? Because each step down, that's all I'm doing. It turns out to be even easier than that once you look at how this tree is structured, but let me just start by showing you sort of the straightforward. I'll read out two of the most straightforward ones. P0, there's only one way to get to P. P0 flows up the tree only one way. You start with P0, we multiply it by 1 minus t, we multiply it 1 minus t again, we multiply it 1 minus t. So P0's contribution is just 1 minus t cubed, right? I mean, 1 minus t P0 is the only thing we're going to get. P3, same thing. We multiply by t, we multiply by t, we multiply by t. T cubed, P3. So we know those guys. The question is what happens here? Because they got multiple branches incoming, right? Well, multiple branches just means that I would have been multiplied by both of these things. One of the blends would have multiplied me by this branch, right? And the other blend would have multiplied me by this branch. So we just need to make sure we do all of them and sum them together. So we have a 1 minus t plus a t, right? And you could think then up again, well, this one's just a t and a t to get to the top, but this guy, he also branches. Well, the crazy thing about this is if you look at the shape that this makes in the triangle, it's actually a parallelogram, right? It's like it's sort of a rectangular shape here, a parallelogram shape, where no matter what I do, if I'm trying to get to P2, I have to take the same number of t and 1 minus t branches to get there, right? I can either go the whole way this way and then shoot down at the end, so 2 t's and a 1 minus t, or I can do one of my t's, then do the 1 minus t, then do a t, or I can do the 1 minus t first and then do the 2 t's. But either way, I'm always doing 1 minus t and 2 t's. So there's just really 3 paths I could take that are all the exact same coefficients. So it's just 3 times the t squared 1 minus t, right? That is how I get to P2. It's just 3 of the same thing. The same is true of this guy. I can take my 1 minus t branches twice and then take a t. I can take 1 minus t, then a t, then a 1 minus t. Or I can take a t and then 2 1 minus t's. So it's another 3, but this time it's the 1 minus t that shows up twice and the t that shows up once, right? And there's P1. This is the equation for a Bezier. That's it. Sum these guys together, that's the entire equation. So literally, if I want to make a Bezier, if I want to make the Bezier this, if I want to change this B, we'll call this, I'm going to call it C, because de Casteljoux is the guy who actually, I think, invented this. I'm not actually sure. But if I want to make a C where I take my P0, P1, T, P2, P3, if I want to make that, it's just the sum of these terms. That is just 1 minus t cubed P0 plus t cubed P3 plus 3t squared 1 minus t P2 plus 1 minus t squared t P1. That's it. That's all we're talking about. You can do this yourself. You can do it at home, even if you are not a professional. That is how easy this is. Bezier curves are so simple. Okay, so what does that actually allow you to do? What does this allow you to do? Well, it allows you to basically implement Adobe Illustrator. I mean, this is Adobe Illustrator right here. That's what you've got. So you can now make tangent handles and programs just like this, where you basically say, okay, I got a P0, and then I've got some P1 up here, which I don't really necessarily draw to the user as if it's another point. It doesn't look like these, but it is just another point. And so all I'm going to do is I'm just going to have it out there that they can grab and move it around. When you actually input those points in to draw the curve, you can just sample, make a bunch of t's, pick a bunch of t's that you're going to sample your curve along, draw it, and you've got Adobe Illustrator. Everyone's happy, right? It's great. But Adobe Illustrator isn't what we came here for, unfortunately. Grass is what we came here for. And how does this apply to grass? There are no curves in the grass. Well, there is a curve in the grass. It's just a 1D curve, not a 2D curve, right? So you are used to seeing these things in that Bezier format. You're used to seeing, this sort of thing with a curve, doop-de-doo, right? That's a curve. But there's another way we might want to make a curve. We might want to make a curve that is one-dimensional, right? So I'm going to draw it in 2D because a one-dimensional curve is not something that you can even visualize. But I'm going to make the curve is entirely in this space actually, and this is going to be the size of the grass, right? That's going to be right here. Well, the size of the grass, I'm going to specify 4 points. They're 1D points, so all they are is a size, right? The first size is going to be the size at the center. I'm going to make that be big, size of center, like I said before. The other point is going to be size at the radius, right? That's going to be down here, let's say. It's going to be essentially nothing, so size of the radius. The other 2 points are still tangent handles. Even though we're in 1D, we can still control essentially what the velocity is of that curve as it moves out over the distance. So I'm going to make this be the distance, just so you can see the evaluation of the function as we go. This is the size function. We pass in the distance, where the distance is basically our t-value, right? Our t-value. Okay, so if it was just a linear, if we were just using our b, and I specified here and here as the inputs, then this is what we would get, right? As we got out to t equals 1, we would get to 0, which is our size of the radius, and as we got back up to t equals 0, we would be at size thing, right? Now, if I want to make this fall off in more of a way like that, let's say, then all I have to do is switch to my Bezier format. So now we're going to input 4 values. We're going to input s of c as our first value, right? So we're going to do our c, p0, p1, t, p2, p3. We are going to input to that in place of p3, that's our size of the radius, in place of p0, that's our size of the center. And now we have these 2 tangent values basically that say what is the speed, if you will, that this is leaving for. It's sort of like saying how fast is it getting off the gate, if you will. So if p1 were set to the same value as p0, right? If it were set to s of c, then that would start us off this way, right? Because we basically have no velocity downwards. You could think of it that way, saying, right? If instead I set it down somewhere lower, if I set it down somewhere lower here, that would change the start of this curve to aim in a different direction. So the lower it is, the faster the fall off will start. The lower this is, the faster the fall off will start. Again, because just like in this example, if you were to move these things far away, you get a much faster moving curve. It's the same exact thing that's happening here, right? You get a curve that's much more, that's kind of moving much more quickly out of that position and achieves a much bigger sort of bend to it, if you will. Now the same is true of P2. That's basically how we land, okay? If P2 is equal to P3, if it's the same value, then we're going to land smoothly. We're going to land this way. So that would create curves that kind of look, who knows what happens here because it depends how we set P1, but that would create curves that kind of curve in like this. They basically have ease out, if you will, right? And this was ease in up here when we set them equal. But if we don't want those, or we want them to kind of land quickly, land hard, like that, right? Then we would set it to something higher. We would set it to something closer to what we set P0 to be. Does that make sense? So we would set this higher if we want sort of a stiffer bounce to it. So you already know how to make the Bezier. We already worked that out. Now you've got how you actually set the values. We know how to turn distance into a t-value because you normalize and clamp it. So putting that all together, you have exactly what you need to make something that interpolates any value over a distance field, right? Very, very, very straightforward. All good. All right, so that's pretty much all you actually need to be able to do if you want to do the thing that I was talking about at the outset, which is controlling how the grass goes, right? How the grass does this. We can do all of these different things. We just looked at how to do those by just setting those inputs to our 1D Bezier, and off we go. All right, let's just go briefly into some other example topics just so you can see how generalized really this interpolation stuff is and how central it is to a lot of the things that you might do. Now, obviously, you can already see, just from what we've talked about already, that animation and illustration, those sorts of things, all use these things. You've seen Bezier curves everywhere. You've seen Bezier curves for controlling motion of things in space, like if you're animating things in Flash or any of that sort of stuff. You've seen Adobe Illustrator, those sorts of things where you draw curves using them. So now that you know the basics of the Bezier, you can leverage that into all sorts of stuff. But that is not even close to all of the places that this general format for things occurs. And what I want to show you is a little bit more general way of looking at all of these things so you can kind of see really how ubiquitous this sort of I had a few input points and then I changed some values that multiplied them to produce new stuff. How general that is. First thing I want to point out to you, I want to point out to you that I could have written this a different way. So b of t equals 1 minus t p0 plus t p1. I could have written this a different way. I have baked into this equation, because of where it came from, because we started with the delta p, because of where it came from, I have baked into this a bit of a constraint. And the constraint is that t is used to multiply both of the inputs. I have essentially imagined, if you will, that I had two other values and then I constrained them. What do I mean by that? Well, let's suppose that I rewrote it this way. Instead of b of t, I'm going to make b of t be equal to b of w0, b of w1, which looks like this. w0, p0 plus w1, p1, right? I want to make it so that each of the inputs gets its own multiplier. Well, just looking at this, you can immediately line up the values and know exactly what each is. If I wanted these to be equal, then w0 would be 1 minus t, and w1 would equal t, right? Makes perfect sense. It's all nice and clean. What is this actually saying about w0 and w1? What am I actually saying there? Well, what I'm actually saying is actually kind of obvious if I plug them into each other. If I actually substitute w1 in for t here, because I know w1 and t are equal, I would get an equation that looks like this. I would get w0 equals 1 minus w1, which means if I rearrange the terms, I move the w1 over, I get w0 plus w1 equals 1. And this is a big deal. This right here. This is really important. Why is this important? It is important because it is a constraint. It is a constraint on this blending equation, this combination, this weighted sum, right, of values that says that the weights must add up to 1. Might not sound that momentous at first. Might not. But you can already see it's kind of interesting. If I just take any two old values and I multiply them by any two old coefficients, who knows what I have? I have an equation. But the instant I add this constraint, as soon as I say w0 plus w1 equals 1, all of a sudden out pops the equation for linear blend. Right? It's a little interesting. What happens if we were to take that a little bit further? What happens if I were to say, making a function here, where I'm going to take, say, a bunch of sets of these, however many I want to, and I'm just going to say that I have sums of bunches of points. As many as I want. Well, this starts to become a very, 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 very powerful, handy little dude. And it shows up in tons and tons of places, which I will briefly tell you about now. But in almost all the places that it shows up, again, you will see this sort of everything has to sum to 1 bit. And I'm going to talk about why that is in a second. But first, let me get on to the uses. So, for example, you may have heard about a thing called barycentric coordinates, right? This gets used a lot. It gets used in rasterization. It's a thing that's basically saying, well, okay, what if I have a shape, let's say I have a shape in the plane here, and it's got 3 points to it, and I want to address this shape, right? I want to address this shape using fewer coordinates than I would actually need if I was representing weights on all these points. So I want to take these points, I want to take all 3 points that I've laid down, I want to write an equation which allows me to pick points inside the shape that has been made. I want to be able to sort of get points in here. But I want to do it in a way that gives me a 2D parameterization of that, right? Because I'm in the plane, there should only be I should only need 2 parameters to specify anything in the plane. But if I was going to write out this equation, w0 plus, the one that I said before, plus each of the terms, like this, if I was going to write this out, Well, I've got 3 different inputs to it. I have my points, and now I've got these 3 inputs, W0, W1, W2. How does that doesn't give me a 2D parameterization, that doesn't give me a nicely addressable thing. What I wanted was something like, a triangle, I want like a UV or something like this. I want to be able to specify 2 values that kind of put me inside my triangle somewhere, and I know that no matter which ones I pick, I always get something inside the triangle. That's barocentric coordinates. Well, it turns out that basically if I just constrain these weights to equal 1, that is exactly what I get. If I solve for the u and the v necessary to give me this constraint, right, just like back here, if I actually do exactly this sort of thing, where I say I want W0 plus W1 to equal 1, well, if that's the case, then we can sort of say, this back substitution here where I say W equals W1 and 1 minus T equals W0, that exact same thing, if you apply it to this equation, gives you the barycentric coordinates for a triangle, right? Makes sense. Okay, I can do the exact same thing for weighted blending of animations and skeletons. So if I'm writing an animation system, right, if I'm writing something where I've definitely got a bunch of animations, I've got something like, I don't know, I've got a dude, right, and I have poses of the dude. So I want to be able to basically take these dudes, and I want to say, oh, I move his arm up here, and I've got, transforms, so I've got transforms at the joints or whatever, and I want to blend these things together. And furthermore, I maybe have something where I've got, the joints in him have like a skin set on him, right? This is, I don't know what this is. Maybe this is a finger, let's say. This is kind of a finger that's being bent upwards. I don't know. It's a very terrible finger. I admit that, and it's fine. So I have these, and I've got vertices on here that are kind of, connected in some way to it. These are also represented by this. How are these things represented? Well, in this case, when I'm doing skeleton animation, I have multiple transforms. I have multiple transforms for my dude. I've got a transform, for example, where his hand is updated. Let's call that T0, and then I've got one where his hand is down, and we'll call that T1. Use the exact same equations to produce T's in animation. You have some value that blends between the two, and you can do, your 1 minus T, T0 plus T1, you'll blend the transforms together. This is how skeleton animation systems work. Now you can sum these out even further. If you have multiple animations that you want to sum together, you switch to the same format. You have W0, W1, W2, W3. You have that same mother equations before. You can use as many as you want as long as the weights all sum to 1. If all the weights sum to 1, then you end up in a scenario where you are guaranteed that you will be interpolating, you are guaranteed that you will be staying inside, much like with the barycentric, the original set of poses that you had. So you won't have the hand go outside, go further this way than it was, and you won't have it go further this way than it was. So the same rules always apply when you make sure that all your weights add to 1. Same is true of this guy. If I have weighted blending, right, you paint in an art package, like you're in 3D Studio and you have vertices, and you weight them to different transforms. So some of it's weighted to this transform, some of it's weighted to this transform, the same vertex shares multiple ones. The same exact things happen. You have the weights, you sum up the transformed versions of this guy using the weights, and out comes the value that you want. Now, again, if you want it to stay between the positions where this vertex would have been when it was transformed by each guy, the weights have to sum to 1. Okay, so why is that? What is with this weight sum to 1 situation? This equation gets used everywhere. You are using this thing where it's W0, P0, W1, P1, and off we go. We are summing up these sets of things, whether they're animations or points or whatever they are. We're summing all these things up, and we're saying that these things have to sum to 1 to give us these nice properties. So, ... Wn, let's say, all of those. We sum all these things up. If they add to 1, we get all these nice properties. Why is that? Why is it that it keeps us within the bounds of the animation, or within the space of the transfer vertices, or within the triangle in the case of barycentric coordinates? Well, the reason is actually fairly straightforward. If I am saying that all of my parameters go from 0 to 1, right, because all the W0s, they all go between 0 and 1, right, just like the T's did. If I'm saying that, so I'm basically saying that they can't be negative, and I'm saying that they all sum to 1. Then what that means, if you think about it in terms of literally just the input values, even if you just think of it, say, in one dimension where it's the easiest thing to think about. So if I have a P0 and I have a P1 and I am combining these two things together, then if I know that the weights have to sum to 1, then the furthest that I could possibly get down this direction would be when the weight for P0 was equal to 1. So when W0 was equal to 1, which means W1 would be equal to 0, I can't get any further this way than that, because that is just the point P0. If I wanted to get any further this way, right, I certainly couldn't move some of the weight. Remember, they have to add to 1, so I can only move values. I certainly couldn't lower W0 and raise W1 because P1 is further in that direction. So the only thing that would do is move the point this way. The only way to get below P0 is to have less than 1 total. I would have to lower W0 without lowering W1. So what the constraint of equaling 1 does is it keeps me from ever getting outside of the boundary, because you can never produce a value lower than your lowest value, because the only way to produce that is to put all of the value into that lower value's weight. And there's nowhere else to put it that will be any lower. The exact same thing is true of the maximum guy. Whoever is the highest in any particular dimension, if I look at that guy, the furthest I can get towards the high end of the number line here is if I add W1 equals 1 and W0 equals 0. That's the only way that I can get all the way to P1. If I wanted to get further away, I would have to increase the amount I was multiplying P1 by, making W1 greater than 1 itself. I certainly can't reduce W1 and move some of that values down to W0, because that would move me in this direction since P0 is less than P1, right? So the constraint on equaling 1, when you sum them all up together, is a very important thing that keeps you in interpolation. Basically what that does, what this does right here, is it says that extrapolation is not allowed, right? That is really all that is saying, because all of these equations would still work just fine if you allowed extrapolation. It'd be totally fine to go outside of P1, right? We could just say set W1 equal to 3, and then we get way the hell down here, right? That's totally fine. The equations still work, but usually you just don't want that, right? I don't want, if I'm specifying these points, you know, back here, even when the very first thing that we did, if I'm trying to specify two examples and get values in between them, I don't want to get out here usually. The artist usually wants to specify the minimum and maximum values at least, right? They're not going to want you to sort of play around with things that are bigger or smaller than the biggest and smallest things that they specify. That is very unusual. And so that is why for most things that we do that are art related, we always add this constraint, because you almost always want it. Okay, and that is pretty much the end of the video. If you want, you can email me here with questions, or you can write to me on Twitter here, if you can read my handwriting. But if not, it's probably at the bottom of the page. Thanks for listening.